Hi everyone, my name is Gaurav and I'm here with my colleague Vincent. We work on traffic management problems at Databricks within the larger core infrastructure group. And today we'll love to talk about our journey of how we fix the request imbalance problems at Databricks, and basically started from rudimentary Kubernetes provided load balancing to something custom, something intelligent that we built specific to custom tailored to our requirements. So before we deep dive into details, sorry, I think small glitch. Okay, awesome. Yeah, before we deep dive into details, let's quickly recap what does Databricks do. So our mission at Databricks is to empower everybody in an organization to have access to all the data and AI, and we want to democratize this access for everyone in the organization. To that end, we have built a unified platform to provide for you to build and provide access for data and AI applications. We are the creators of a lot of open source technologies such as Apache Spark, Delta Lake, MLflow, and Unity Catalog, to name just a few. And the company has been growing rapidly over the last few years. Last year, we grew more than 65% year over year at a revenue run rate of about $5.5 billion. Today, we serve more than 20,000 plus customers, and a majority of Fortune 500 companies are our customers right now. And to power this kind of business growth, this scale, we operate a very large infra fleet distributed across the globe, running highly distributed and latency sensitive systems. Today, we are deployed in 3 clouds, AWS, Azure, and GCP, in more than 70 plus regions, where we are running north of 1,500 clusters across our control plane and data plane components. And to power this kind of data processing requirements from our customers, we have to deploy millions of VMs on a daily basis. Now you can see at this kind of scale, even a smaller inefficiency in a system can become very visible and cause major problems for us. On the traffic management side, we deal a lot of problems around like how do you route traffic across these regions? How do you channel traffic from ingress to a particular service? How do you do like communication across clusters, across regions, and now even cross clouds? But for this talk, we'll focus largely on how do you ensure that the communication happening within a cluster is seamless, and we are effectively load balancing traffic among all of the pod services running. So let's get started. Our story begins with bad SLO violations and incidents, right? So there was a time, long time ago, when product teams would see a lot of 5xx errors or higher P99 latency. And it was particularly harder for them to debug and understand what was going on, largely because these errors would be like intermittent and come and go, and they're not adept at like figuring out what's going on behind the scenes. And this wasn't happening for 1 or 2 services. This was a pattern that was happening across the board for various R products that we own. And what is the first instinct, right? When you see these kind of spiky errors, like I'm sure a lot of an audience will correlate with this thing, that the first instinct for a lot of people is that, hey, might as well add some more resources to the service. Let's add more CPU, some memory, or maybe even worse, let's add more pods. But where does it lead us, right? It leads us to highly provisioned services more than what they require, and then you're wasting resources at that point in time. So even though the services are over-provisioned, but the underlying problem is still not resolved. Like we still don't know what's going on, and just by throwing more resources doesn't get us where we want to be. And that's where we come into picture. We also started to engage with the product teams, trying to understand what was happening behind the scenes, right? So one of the patterns we started to observe across these incidents was, like as you can see in this graph, the top one, all these different lines are QPS going to different pods within the same service. So what we started to learn that the traffic going to individual pods is actually not uniform. So there is a lot of variation. And this is these are two pictures from two different services. And in some extreme cases where we actually saw some incidents happening, the traffic the traffic skew was north of 4x, 5x to some of the pods. And now when you have that kind of skew, you start to see a lot of like latency spikes and errors are going higher. Okay, so now we understand at least what's happening, but then what is the root cause? Like why was this happening in the first place? So that's where we learned that Kubernetes actually does not balance your request across the pods. What it balances is the connections. It's the connections that are distributed, not the requests. And why so? It's because the load balancing in Kubernetes happens when you try to establish a connection. At that time, it's the kernel which is going to pick one of the pods for you from the list of the pods that kube-proxy has already coded somewhere in its control plane. So you will get a very uniform connection distribution with Kubernetes, but that's not sufficient, right? Because a lot of our traffic at Databricks leverages gRPC, and gRPC is built on top of HTTP2, and HTTP2 multiplexes your request over the same connection. So now, depending upon the shape and size of your client, some of the connections might have like thousands of QPS going, and other pods are getting like very minimal 10 QPS, for instance, right? So even though the connections are very well load balanced, but the requests are not, and that's largely because of the issue that we understood with the Kubernetes load balancing. And it gets worse, right? So the diagram I have here is very poorly drawn. We have a client, it has two connections to each individual pod, right? So now, what happens, let's say your pod A, if you believe my service in stress, you're gonna go add another pod. But the moment you add a pod, it does not move the connections. Connections stick to the pods which they already are, right? So you added another resource to the system, but it does not actually help you mitigate an issue that you are probably facing at that time. And over the time, it's gonna get worse. What if pod B goes down and pod E and F comes up? Now you have your previous connections are still gonna be with pod A and C or maybe D. Only the new connections will start to get balanced, and it'll take some time maybe for you to get the load balancing over the time. But this problem only gets worse. And if the connections are imbalanced, in that case, your requests are gonna get further imbalanced, right? So the problems keep on getting worse and worse over time. Another case could be like some cases, services team would have this slow rollouts. Like when you are booting up a service, you want to slowly onboard new pods. Now, what if a client is waiting to establish 50 connections? All of those are gonna go to the first pod that comes up, and the rest of the pods are not gonna get any traffic. So this is where we have to be very careful to understand our system and then configure our services accordingly. Yeah, so now we understand the problem, we understand the root cause. So we tried to fix it with multiple approaches. So here are some of those we tried. And like, for example, first one is, let's just reset the connections and force some distribution of the connections. Or maybe we can use a headless service, which can help us get some client-side load balancing. Or we can just start running a service mesh in all of our clusters. Let me walk you through the pros and cons of each one of those approaches that we tried and why did we not ended up going with any one of these eventually. Our first solution was to, hey, let's reset connections. Let's reset connections every X requests or maybe X minutes, right? So very simple idea. We actually tried it in production and results were good. Like we started to see slight improvements in the request distribution. It was still not where we would ideally want it to be, but it did buy us time, right? So it was a short-term solution, worked pretty well, but then there were enough shortcomings of this solution also. What we have just done with this approach is we are only still distributing connections at best. The underlying root problem of requests getting distributed is still not solved. Second, there is a reason HTTP2 want to multiplex over the same connections. Because if you start churning the connection, that's an expensive operation, right? So If you churn, you have higher CPU and latency issues start to prop up again. And lastly, what we figured is it's very hard to tune this approach. Like, after how many requests I should reset, right? If I delay too much, then you have the same problem, right? Where you have, it's happening too infrequently, the request imbalance is gonna come up. If you start to do it too frequently, in that case, you have to pay that cost of like CPU overhead and higher latency again. Second approach, the headless service. It's actually a lot of people do this in production environments also. It's a very simple, trivial fix. Like, stop using cluster IP that Kubernetes provides, which essentially gives you a virtual IP address. Set cluster IP to none, and this will give an impression that we have kind of stopped using default load balancing. And you go to DNS. Hey, I want to talk to service B. And DNS is going to give you back all the pod IP addresses. Now it's on the client to do the load balancing on its own. So we effectively move from per connection L4 load balancing to per request L7 load balancing. And that's a very good step in the right direction. And it's very cheap to implement this also. However, this also has a lot of cons, specifically around the DNS caching. Now, when you are asking DNS to resolve this URL for you, it's giving the list of pod IPs instead of a single pod ID that you'll get earlier back. And DNS libraries tend to cache, right? You don't want to be hitting DNS on every single request path. The moment you start doing, your DNS is under load, and we have had dealt with our own set of problems with DNS at scale, right? So this was a major concern that we couldn't even run it in production at a larger scale. And lastly, when you start doing this, we are effectively started to use DNS as a control plane. Now, DNS is not a control plane that you can configure, you can change, you can't modify as per your own requirements. So we started to have some advanced use cases that I'll talk about as we progress, which could not be supported by this as a possible solution either. And lastly, the third approach was, hey, let's use service mesh. So what service mesh will give you, you will start running Envoy proxies on every node. But then it comes at a cost. Like, even though we are running a very large fleet, even for us, the cost of operationalizing these proxies on every node and also add a hop for every service to service communication, there was a very high cost to pay. And we didn't have enough appetite to sign up for it at that time. So we didn't go with the service mesh approach also. And we also had some past experiences which guided our decision not to move in this direction. Okay, so coming back, so we had these three approaches. None of them really solved the problems that we intend to solve, or maybe they partially solved it, or added complexity, or could not capture all the signals that we would want our load balancing solution to have. So this was a time when we took a step back. It was like, hey, I think we need a more intelligent solution. And we should step back and review all the requirements that we would want to have in our load balancing solution. Right? So let's quickly take a look at all of those requirements that we wanted to see in our system. First and foremost, we need fairness. We want uniform request distribution. We don't want to see any hotspots. No pod should be getting overwhelmed with traffic. Second, we want efficiency. Efficiency both in control plane and data plane. Now, what does it mean? Right? A pod comes up and goes down. Our load balancer should immediately know, and there should not be any lag. That's the control plane part of it. And the second, we don't want to add any additional network overhead because the systems that we are dealing with are extremely sensitive to latency. So that's also a big no-no for us. And lastly, this is where the intelligent part comes into picture. We wanted our load balancer solution to be smart to know, hey, this pod is experiencing some problem. Maybe this pod is on a bad node, or maybe some network connectivity issue on that pod. This is a bad pod. I don't want to send traffic to this one. Another thing which is very specific to Databricks is that purely for durability concerns, we deploy each service across multiple availability zones. Now, if you have your client and server both deployed across 3 availability zones, you start to have a lot of this cross-zone traffic going on. And when you're sending cross-zone traffic, you are signing up for more latency. You're also signing up for additional costs that you have to pay to the cloud providers. So, like after reviewing all of these requirements, one thing was getting more and more clear to us. Even though we wanted all pods to be equal, all pods are equal, but some pods are more equal than others. That was our guiding principle to how we designed our system. And with that, I'll hand it over to Vincent, who will walk us through our final solution. Thank you so much.
Thanks, Gaurav. Yeah, so extrapolating from all of these requirements, we were able to identify key features of kind of the end-to-end architecture that we wanted to eventually build out. So in order to minimize service discovery latency, we looked at all kind of the failures in terms of what the DNS-based solution would have given us. And we realized that in order to actually be able to propagate this information to clients as quickly as possible, we needed something that would at least be push-based instead of pull-based. In addition, in order to minimize impact to the data path itself, we were motivated to avoid a solution that would have intermediary proxy hops, and we wanted to have the client libraries drive all the decision-making. And going further, we wanted our solution to be as flexible as possible. So in addition to things like pod load, pod health, zonal metadata, or other metadata associated with pods, we wanted a way to be able to expand the system over time and express both real-time signals that would churn very frequently for every target service pod, along with static signals, signals that would be more static and constrained to the lifetime of a given pod. And so it became very clear to us just looking at all of these requirements that we wanted to have a lot of customization throughout our stack. We wanted to not just have a custom control plane that would be able to just drive some of these decisions centrally, but also we wanted the flexibility to be able to make our client libraries make all the decisions. And we got a little bit lucky here because internally within Databricks, a lot of our services were already running under a few homogeneous frameworks, and this kind of pushed us in a certain direction. So on the ingress layer, for all of our ingress traffic coming in, we were using basically just our set of open source Envoy proxies. And so for Envoy itself, Envoy supports this discovery protocol natively known as XDS. And while we have a little bit less customizability in terms of how we can configure Envoy itself, we found that XDS was very suitable for all the needs that we expressed previously. The actual payload for the XDS protocol was push-based and kind of subject to whatever the Envoy proxies decided to subscribe to. And the payload itself was quite flexible. It was basically just an encapsulation of IPs and a set of metadata associated with every IP. And one key thing for us that we realized very early on is that even if we wanted to move away from the native Envoy proto, known as cluster load assignment, the XDS protocol itself supported just sending any sort of flexible payload. So we could decouple ourselves from the actual Envoy proto if needed in the future. And so that brought us to our kind of other section of traffic, our internal service-to-service traffic, which didn't necessarily speak this Envoy protocol. We didn't want to bring up all these Envoy sidecars on every node either. But all of these were primarily Scala services. We were kind of born out of Spark as a company, and this kind of grew into how we handled a lot of these control plane services. And we kind of standardized all of these Scala services as well on a uniform framework known as Armeria. And one nice feature was that we had quite a lot of potential customizability into how we wanted to build on top of that stack. So we had the ability, even though we didn't support it immediately, to actually support the XDS protocol and whatever sort of client-side integration we would want into the service-to-service traffic. So what did we do with this? We decided to prototype. We built out what was called an endpoint discovery service, which is the canonical name for the protocol that Envoy expects to speak for this type of IP delivery. And we decided to start sending this push-based protocol and propagating these endpoint IPs into Envoy and Armeria. And it was very important to us that we didn't try to reinvent the wheel. We wanted to build something as quickly as possible. We were running into these problems with bad request distribution, and we wanted kind of an immediate solution that we would be confident in, that would be robust, and that we could roll out as quickly as possible. So other than the load balancing, everything under the hood for Kubernetes in this domain was working quite well for us. And we didn't want to reinvent the wheel. We didn't want to rebuild that. And so even though we had this endpoint discovery service that would send kind of its own protocol over to our subscribing clients, the ultimate source for our control plane was still Kubernetes under the hood. Within EDS, we would just subscribe via watches to the Kubernetes API service, and everything would be derived from the resource contents of the endpoints and services stored within Kubernetes itself. But this was only one half of the problem. Now that we had this control plane, now that we had the ability to distribute these IPs over to the clients, we still needed a way for the clients to be able to drive intelligent decisions. We still needed a way for the clients to be able to distribute requests in a way that would ensure reliability of our backend servers. And so we wanted to start simple. Even though we had kind of motivation to make this more intelligent in the future, we made an initial wager that, hey, if we iterate from here, if we start out simple and just do something really dumb, we just round robin across what we send to, we can still probably get a pretty good improvement over what we had previously. And so you get kind of the expected result. You get a very even distribution of requests across all your server pods. We ran this across our various test beds to make sure integration was correct. We rolled this out across our various deployments. Everything was fine and dandy. Before things were imbalanced, now things were balanced. Okay, perfectly great, we're done here, right? Unfortunately, that wasn't quite the case. We immediately started seeing that there were various problems that this didn't quite handle correctly. And one very interesting problem that we quickly observed was that on every rollout or release of a service, we started seeing these upticks in errors associated with the timing of every release. And so we realized that this was very correlated with every new pod. For every new pod that came up, when we started sending requests towards it, it started exhibiting symptoms of degradation compared to pre-existing pods. We would find higher latency, we would find higher error rates, and we realized there was a code start problem that was previously hidden from us. And that even though we had solved the previous class of errors that we were trying to handle of request imbalance, we had uncovered some potential new classes of errors that we needed to handle. And so in the old world, where every client was just sending to these sticky connections and unable to detect that this new pod had come up until the old connections had expired, this type of lag between a pod becoming fully ready was kind of hidden from us because they weren't even receiving requests in the first place. And paradoxically, it was almost as if clients were now discovering pods too fast. As in, even though they were healthy from the perspective of service discovery, even though they were healthy from the perspective of Kubernetes, they were still not as healthy as other pods. And so diving further back down into this, we realized that there were whole classes of other types of errors that we now had the potential to avoid. For example, just naively sending X requests to every server in our target backend, we realized that there were multiple cases where there were pods that were not quite as healthy as others. Just like the rolling restart or release case of code start, even past that in stable state, we would encounter cases where a given pod would become overloaded in a way that was completely unrelated to the requests that it was receiving. It would start sending errors, and we realized that perhaps it would be good to try to bias away from these pods, both from the error rate perspective, from the latency perspective, and from other kind of symptoms of overload. And so kind of going back to the requirements that we had previously, we asked ourselves, was our goal to actually equally distribute these requests? And so the answer that we gave ourselves was actually no. We don't actually want to equally distribute these requests. What we want to prioritize is the reliability of our services. We want to actually maximize our client success rate. We want to maximize our server stability. And we want to be able to efficiently utilize the capacity that we have at hand. So it was important to us, even though round robin gave us a pretty good improvement over our old world model of sending based on connections, to not just distribute requests uniformly, but before we actually wanted to roll this out, we wanted to distribute them in a way that would bias away from these overloaded pods. And so the first thing we tried was to, there we go. The first thing we tried was to bias away from pods that was exhibiting high CPU load. And so we wagered that if a given pod is exhibiting high CPU usage relative to other pods, it's probably a little bit more overloaded than them. We can bias away from them in a weighted round robin fashion. And so we just throw some math at it. We look at every pod, we assign a score to them, and we try to send away from them. But unfortunately, it still was not enough, at least from the perspective of what we wanted to optimize. And we realized that CPU as an indicator was a little bit of a mismatch of exactly what we were trying to measure. To start with, it was a little bit of a trailing indicator. The way that we measured CPU was in terms of the amount of shares that a given pod was using over a historical window in the past time. And so this didn't always necessarily measure present overload, and it wasn't always a good indicator of future overload either. The other problem for us specifically was that in order to try to get this out as quickly as possible, admittedly, we relied on a separate metrics export source in order to grab this information. And so from our control plane, we would contact our actual metrics system. And we realized that the frequency at which this was scraping the relevant pods was misaligned with the frequency at which we would want to detect overload. And finally, we realized that this didn't always capture all potential causes of overload. Even if a given pod was exhibiting relatively low CPU usage from its own perspective, it could still suffer from symptoms such as noisy neighbors, where the node it landed on may be fully overloaded compared to other pods that are exhibiting the same amount of CPU usage, but perhaps have a little bit more room to burst. And it was blind to other types of problems, such as network blips or logic that wasn't particularly bound to CPU, such as memory usage patterns. And so quickly, we realized that CPU failed to capture everything we wanted to optimize for. And so again, we went back to the drawing board. And we wanted to see, okay, in this case, what is a more perhaps indirect way we can capture all types of overload? And after trialing a few things, we settled on a power of two choices based solution as something that would work well for us. And so for those that aren't familiar with the overall algorithm, it's very, very simple. All it really does is from the client point of view, you select two targets. You assign every target some score associated with them. And for the two targets that you have randomly selected, you just pick the one with a better score amongst the two. And what's very nice about power of two choices is that it's incredibly simple, it's incredibly cheap, both from an algorithmic point of view and also from an implementation point of view. And it's also very easily extendable. So when we started reusing power of two choices, we started with using pending requests as our main source of this scoring. And we found that it indirectly captures signals such as a pod being overloaded just by the sheer nature of it being slower to respond to requests. But as we iterated further, just having this simple score that we could tweak, we were able to find opportunities to add things like accounting for latency, accounting for error rate, and we were able to continue to iterate further to build a more robust solution. And finally, unlike something like a naive least requests algorithm where you always send to something that has the least pending requests, and unlike an algorithm like weighted round robin where you assign static weights, the non-deterministic nature of power of two choices just naturally avoided problems like thundering herd for us. And so we decided to roll this out again, sent it through our testbed, sent it through our production services. And just like round robin, just like a random distribution, we found that in the stable state, this gave very good results. The request distribution from before on top and after on the bottom, we found that everything became way more stable. And not just on the request distribution end, we found that this gave us great gains in terms of the latency stability of our various services. And just by increasing the stability of our expectations of all of these relevant metrics, we were able to find that just automatically the way that we were auto-scaling our services, across the board, the average size of our fleet decreased by around 20%. So we actually got a lot of cost and efficiency gains from this as well. But more importantly, beyond the stable state, as mentioned previously, we were able to use power of two choices as this base foundation that we could keep building on. So over in this graph, you can see a very basic test that we were running where we would just have a set of services receiving traffic from a set of clients. And we ran this through two sort of base implementations of power of two choices. One that was just naively using these requests as its metric in the green, and one that was using some historical error observation as part of the bias to our scoring in the yellow. And through our testing, we were able to find that this greatly improved the robustness of our services to hitting errors, to hitting latency. And this was just one way that we adjusted the score, and just keep on, the ability to keep on building on top of it was very beneficial to us. So to sum up kind of our journey to how we moved away from Kubernetes load balancing to our own load balancing solutions, one of the key takeaways that we had throughout the process was that one thing we quickly realized was that default Kubernetes load balancing does not scale well as you start building out your system. And even though it works very well in the short term, understanding the abstractions that Kubernetes provides you and the limitations that Kubernetes has allows you to identify where you can optimize and where you can inject even very simple things that still perhaps rely on Kubernetes, but allow you more freedom to actually customize your internal control plane and data path. And finally, we found it was very helpful to aim for incremental improvements throughout the process. Even though we found that there were a lot of gaps with our initial solutions and initial attempts to try to replace our initial solution, they helped us uncover what exactly these gaps were, and also gave us stop gaps for potential improvements in the short term. And so that kind of concludes our journey through load balancing here. We still continue to iterate and improve on top of what we have here. But essentially, if you have more interest in seeing more details about what that looks like, we do have a little bit more detail in a blog that we have linked over here in the top right. And we can open the board to questions here.